Alright, let's talk about matter waves. We have already learned that the momentum of a photon is h over lambda. And just to be clear, some people often wonder, how can light have p? Yes? Because we know p is mv. But Einstein already taught us that E equals mc squared. So energy and mass are basically the same thing. They're different expressions of the same thing. So that's how we can have, instead of using this classical formula mv, we can use a different formula here. So we've already learned that momentum of a photon is h over lambda, and light can act like a wave, and it can act like a particle. And then de Broglie decided to turn this around. He hypothesized that if light could be both, why can't matter? That means that matter would have a wavelength. And doing a little math, h over p. And this is known as the de Broglie wavelength, this formula right here. Whoopsie. Later it was proven to be correct. It was proven that matter could have a wavelength. We know this is the double slit experiment, with actually two little slits, and we're shooting electrons at them. They also did this with a crystal structure. So if I have molecules in a crystal structure, very organized, if I shoot electrons at these spaces right here, whoops, if I shoot electrons at these spaces, the electrons will diffract, and they can actually measure these distances and work backwards to find out the spacing between these atoms in a crystal. This is a method that they still use today to measure the distance between atoms in a crystal structure. So this is another experiment done just a couple years after his hypothesis. They did this experiment with crystals and got it to work. So why don't we see the wave properties of matter around us? Well, here's the formula, h over p. Let's think about a bowling ball. Let's say its mass is 10 kilograms. Let's say it's moving at 3 meters per second. This is 6.63 times 10 minus 34 all over 10 and 3. And this number is going to be super tiny. Yes? Lambda here is going to be super tiny. And if we compare lambda to the bowling ball itself, it's going to be ridiculously small. So therefore, that's why we never notice wave stuff happening, because its lambda is so much smaller than itself. If we're going to want to see wave-like properties from matter, we need lambda and the object to be in a similar order of magnitude, or we're not going to see it. So that's why we start talking about electrons, because the wavelength of an electron and the electron itself are similar in an order of magnitude. So his idea worked so wonderfully well. If we go back to even Bohr's model, which we know to be incorrect now, if I have an electron here and it moves to a higher energy level, n equals 1 to n equals 2, it never actually is in between. It literally teleports to the next place. It can never be seen on its way there. Yes? It's just boom, it's at the next level, boom, it's at the next level. So electrons can be found only in specific energy levels. Yes. And this is fantastic because his model explains this very, very well. His model gives a very nice reason for this. If an electron is a wave, it must fit its lambda perfectly around one orbit as a standing wave. And we might remember a standing wave as these waves that these parts are going up and down and up and down and up and down, and there's nodes here. Yes? If you think about an electron as a standing wave, it's perfect. So here's a standing wave, and there's an equal number of wavelengths all around. In this diagram, there is not, right, like node is not meeting node, crest is not meeting crest. Right here I've got a problem. So this would not be an allowed wavelength of an electron. This one would. Here's a really nice diagram of it. Here's n equals 1 is 1 lambda, and that would be the circumference of the orbit around this nucleus. If n is 2, I would have 2 lambda, and that would be the circumference of this n equals 2 orbit, and then 3 and then 4. So this diagram is a really nice one to explain why electrons are standing waves, and the fact that they're waves works perfectly to explain what's happening in Bohr's model. And that's our look at matter waves and de Broglie.